Welcome everyone to the week 12 tutorial session. I am Rati Ludhani, pursuing PhD at Department of Mathematics, IIT Bombay. Today we will discuss assignment 2023 of week 12. So let's begin. Let A is equal to 110011101. Then what is the dual RSK of this matrix that we need to calculate? So as you know, the process is we have A. Yeah. What first we will find the byword or bivector. So what will it be? The bivector.
1 1
Hmm.
1 1 1 2
1 1
2
okay.
2 1 2
Yeah, 1 2.
2 2 2 3
Yeah.
3 1 3 3.
Yeah, exactly. So it's just we need to write the row number and column number. So this is the row number and this is the column number. And we will repeat it how many times the number is written to be. So as this is just 0 1, so we just need to write it either it will appear or it won't appear. Okay, so we have the bivector. Now what we need to do, we need to find dual RSK. And one more thing, we will get dual RSK like the corresponding, as you know, we will get insertion matrix and usually we write P and Q, where P and Q are semi-standard Young tableau with the shapes, with shape of P is equal to shape of Q dash. So Q dash is the like the rows will be columns and columns will be rows. So we'll just invert it in that sense. So shape of P will be same as shape of Q dash. So this is DRSK. This is SSYT because A is with the entries 1 1 1 1. Like there is no entry which is bigger than 1. So that's why we you can try if you want to. You can try with, like, for example, 210. You can try with the bigger number and try to find dual RSK. Then you won't be able to get Q and P to be the SSI like semi-standard Young tableau. So in the process, if you try with number bigger than like if the entries are not just 0 1 or something else from the integers, then there you won't be getting semi-standard Young tableau. Okay, so just about the thing. Now, so what we need to do, we need to find the dual insertion. So insertion tableau. Sorry. I think AUX, yeah, and recording tableau. So this is Q, and whatever we right now we'll get, we'll write it P dash, and this will be corresponding to corresponding to whatever we'll get, that won't be SS semi-standard Young tableau, but when we invert it, then it will become or maybe transpose it, it will become semi-standard Young tableau. So firstly, this is 1. So like there is nothing to begin with, then we can insert 1. We'll get 1, and the corresponding row vector is corresponding row number is 1.
1.
Yeah.
1.
Exactly. And now we will insert 2, right? So this number, then what we will get? 1 2. Nothing to
1 1.
And next to what we will get?
1 2 next row 2.
Yeah, exactly. So the difference between dual RSK and RSK is, like, we are allowed to replace the same number also, not just the bigger number. So if it is equal to 2, then we will replace that also. So this is 2. So when we inserted 2, then this became this 2 and this 2 has been replaced, and 2 bumped out and went to the next row. So that is this 2.
Here we see A less than or equal to AI.
Sorry, which one?
A less than or equal to AI. In
Yeah,
RSK we use
exactly.
just greatest number only.
Yeah,
Here equal and the greatest number also.
exactly. So uh, and the recording tableau will get 112, so
Two.
corresponding to this. Now what we are inserting? We are inserting 3. So you have
3.
1 2 2, sorry, so I'll just remove it and write 3. So when we are inserting, so 3 is as you can see in the first row there is just 1 2. So 3, where will 3 go? 3 will just come here because
First.
there is no number which is bigger than or equal to 3, so it will just stay with the new box. So 2, and here the recording tableau will see 2, right? Next one, next we are inserting 1. So what will we get? So now when we insert 1, so in the first row, as this is dual, we will just look for AI which is equal to or bigger than 1. So as you can see, 1 is there, so we can just pump out this one and we'll get this, and this one will go to the next row, and then 2 will be replaced by
And
1.
2.
Yeah,
Third row.
and third row, exactly. So you have 1 1 2 2, and the last row will be yeah, we inserted 1, so the corresponding number is 3. Now we'll insert 3.
3.
So where will it go? So in the first row,
First row 3 comes to second row.
yeah, 3 will be bumped out and it will go to second row, and we'll get 1 3, exactly. So 1 1 2 2 3, and the
And 3.
corresponding,
Second row
yeah,
3.
3, exactly. So
And P is we interchange. Rows are
yeah,
columns, columns are rows.
exactly. So what will P be? P
P
is,
equal to P dash. P dash.
yeah, so this is P dash we are calling, as we started with
Mm.
that. So P will be what? P will be 1 1 2
1 1 2
2
2 3
3
3.
3. So first row, second row, and third row. And here Q will be exactly this only.
Same.
So yeah, as you can
Same.
see, this is same. So
Uh,
we got same 1 1 2, this one, right?
this one.
Okay, nice. So I hope this is clear then. Very good. Okay, let's move to the next question. Let A be,
Ma'am,
yeah.
second or 1 minute. Second question. Using this option, I did. But exam is pen, paper, descriptive type. They ask question only. They won't give options. So,
Okay.
ma'am solved with question how to get the answer matrix.
Yeah. I'll not use the options. I'll directly do using
Okay, ma'am.
this. Yeah. We
Mm-hmm.
did it last time also without options. We'll do
Ah,
we'll do without options only, yeah.
okay.
So we have this 2 3 3 4. Now so as you can see, we have this DRSKA. So this is P, this is Q. So we should start with P dash. P dash is equal to 1, sorry, 1 2 3 1 3. So first row, second row, third row, fourth row. And this we have 1 1 2 2 3 3 and 4. So this is Q. So we have both of insertion tableau and recording tableau. But what we need now the bivector to get back our matrix. So how should we do that? What we will do, will again, like, so as you can see how many entries must be in the matrix. So firstly there are Q is the row vectors. So what I can try, so the bivector, we need to start bivector of A. So something this, and q, what q is telling, q is row vector. So we as we can see, 1 1 2 2 3 3 4, there are like two ones, two twos, two threes, and four, one is 4. So in the bivector we always write it in the increasing order, so weakly increasing order. So the row number I am just writing, and that is definitely going to be like this only, right? So Q is just the recording tableau that records the row number, and we always write it in the weakly increasing order. So I can write the row vector as this. So first row must be this, right, in the bivector. Is that clear?
Yes, ma'am.
Now what we need to find, we need to find the column number corresponding to this. That we need to find out using P dash and Q. Okay, so as if we see this, we can say that the matrix is so this is 4, right? So 4, like the fourth row, so there must be 4 rows. Now how many columns we must have? P dash is with the entries 1 2 3 1 3 2 3. So the highest number we are going till 3, right? The highest number is 3 in P dash. And what P dash has, the number of P dash has the column number. So column number we can go up to 3. So there must be 1 2 3, 3 columns, right?
Yes, ma'am.
So
Yes,
we
ma'am.
know what is the size of a matrix, and as I said earlier, this process RSK and dual RSK does not record if there are any zeros in the end, like there is any row with only zeros in the end, and they or maybe there is a column only with zeros in the matrix, that it does not record. So we are assuming that it has not been asked, so you always write it in the form of uh, with non-zero rows and non-zero columns in the end. It could be there in between, but not in the end. Okay, so that's why the matrix has this size right now, we can assume. Now let's try to find 1 2 3. So we'll try to find the bivector. So I'm just writing it again. 1 1 2 2 3 3 and 4. So as there are 7 entries, so I'll start with the 7th step, 6th step. I'll go back, okay, to find out our bivector. So 7th step, let's say this is 8th step or whatever, so let's call it 7. Now what we will do, we will look at Q, and from the end we will start. So 4 is there, so 4 must be removed, that must be the new box. When 4 corresponding to 4, we have 3. So 3, now we will remove 3, but now we have to go back, right? So going back means, so you are looking for, so this is your AI now. So we are looking for A such that A is less than or equal to AI, right? So this is our AI. Now we are going back. So when okay, so I'll do it for one step at least properly. 2 3. So 3, let's remove 3. So uh, you inserted 3 here, okay? Now when you go back in this row, so this is your AI, and AI, so you are looking for A. So as you can see, this is less than 3. So what would have happened? This
We remove.
this would have been 3, and you must have inserted 2 in this row, right?
Yes, ma'am.
And now this is this. Now this has become your AI. Okay, so now we are looking for 2 to be inserted, like from where 2 must have bumped out in the from this row. From what, that we need to figure out. We again look for a such that a is less than or equal to ai. So for 2, 1 must be that number, right? So we will be
Yes,
getting,
ma'am.
so this must be 2 and you must have inserted 1, right?
1, 2.
Now from where one would have come from, the now we have to go to first
First.
row. So yeah,
First.
again we will look for a such that a is less than or equal to ai. So that must be that number. So 1, let's, this is the new one and you must have inserted 1, right? Because this is same.
Mm.
So
Mm.
so 1 must be the corresponding number. So you'll get 1. Is that clear?
Yes, ma'am.
Okay, great. So I'll remove this and let's write the 7th step. We get 1, 2, 3, and now this was 2, this
2,
was 3,
3,
and this is 3.
3.
And this is, and corresponding to that recording tableau is this. Okay.
Mm.
Okay, let's see 6th step. Now we again look for the bigger number 3 and 3. So there is this 3, there is this 3. Last time also I said, like, we have to check whether which one is the one which must be which should be removed, and like this. One more thing, again, like this, right, the right box, one should be able to prove that the right box is the one which must be removed in which must be removed first. Okay, that can be proved, but let's try again by checking here. Okay, so let's try both the numbers. Let's try this 3 first. So if we remove this 3, okay, if we remove this 3, so corresponding to that we have 3, right? This 3,
Yes, ma'am.
okay, yeah, okay, so I'll write it once again and do here. So 3 would have been removed. So corresponding to 3, now you must have, so 3 must be bumped out from the second row, and second row is, so you will look for
3.
a is less than ai. So this is your ai, so a must be the highest number you are looking, the highest number a is such that a is less than or equal to ai. So 3 must be bumped out, like yeah, so this 3 must be bumped out and came to the third row, but from where it must be, from this place. So what you must have, this 3 should be so this 3 will go, and what would have happened, so you must have inserted 3. Now you will go to the first step, and there if you again see, you have 3 again. So you will bump out this 3, and this 3 must have been replaced. Okay, so corresponding to 3, you got 3. I'm not saying this is correct right now because I don't know, like with both of these we will check. Okay, and one more thing, the matrix is 0 1 matrix, that we need to make like we need to remember, because the bivector corresponding to a, we should not get the same combination, because if we got same combination, for example 3 3 is again 3 3, if we got 3 3 again, then it is of no
Not
use.
correct.
Yeah, this is not correct, because a is 0 1 matrix, so that must be 2, otherwise the entry must be 2 corresponding to that. Okay, so let's see if we got this. So you have 1 2 3 2 3 in the fifth step. Okay, and corresponding to that you have this. Now next you will remove this 3. So when you will remove this 3, corresponding to that you got this 3. So this you remove from here, and then it will go to this number, this row,
3.
and again you have the same number,
3.
so that must be 3. So the number you must have 3 again, but that is not possible, right? So you cannot get here again 3. Is that clear?
Yes, ma'am.
Okay, so you have this 1 1 2 2 3 3 4, and I'll try to keep it in the notes if I can prove this part that the rightmost is the one which we should remove first. Okay, but you can try by your own also. Okay,
Yes, ma'am.
so this is not okay. Now we need to what we must be doing, we should remove the other three. Okay, so we have yeah, this three we will remove. So we got 1 1 2 2 3. Now when we remove this 3, so this 3 will be gone, and this must be bumped out from the first row by this 3 only, as we have just seen. So this is 1 1 2 3 2 3, and the number must be 3. If you want to write, you can write it in this tab like 3, and here we bumped out what, 1. Okay, yeah. Now let's move to the next step. Now this 3 we are removing, okay, because that's the only choice right now. So you have if you bump out this 3, like if you remove this 3, so corresponding to that we have this 3. Now if we remove this, now it must be coming from 1 2 3, and here this 2 is there, right?
3.
So this must be replaced by this 3, because we are looking for a such that a is less than or equal to ai, and ai is 3 right now. So we'll get 2. So we must have done that. Now this 2, now from the first row 2 will be replaced by, we will look for a such that a is less than or equal to 2. So the highest of that, the highest number with such property, so that is 2. So what we must be having, 1 2 3 3, and 2 must be inserted, right? Is that
Yes,
clear?
ma'am.
So 1 2
Yes, ma'am.
3, okay, 1 2 3, and this was 3. So we got 2, and that is okay with our condition, because we don't want to be the rows to be repeated, like this part to be repeated by in the bivector. Okay, now again the same case, this one or this one. So you can check that this will not work, this 2 will not work. So what you can do, let's try with this 2. Okay, unless you prove it, don't assume that this is a true statement, because I have not tried it, but I'll write it in the notes which I'll share. Okay, so with this 2, if you remove if you remove this 2, we'll get 1 2 and 3 is already there. This 3 is just be removed because this is in the first row, so we would be having 3 here. No, so not 6th step, this is 4th step, this is 3rd step. So we have 1 2 now the next number is this, so 3 must be the number which we need to see. So ai is 3, and in the first row we'll look for a such that a is less than or equal to 3, which is 2, the highest of that, the highest number with such a property. So we'll have 1 3, and 2 must have been bumped out, so we get this. So we got 2 here, and now for 1 1, it's just a simple thing. We have 1 and 1 because 3 must have been inserted, and with the first we have 5. Okay, so 3 and 1. Is that clear now?
Yes, ma'am.
Okay, so let's see what we get from this 1 3. So in the first row we have 1 1, and this is 0. In the second row this is 2 3, so 1 1 0, and in the third row we have 2 and 3, so 0 1 1, and we get 1 here and 0 0.
0 0 0.
Yeah, so which one is this? The first one.
First one.
Yeah, right, first one. Okay.
Yes, ma'am.
Yeah. Okay, let's see the next one then. True or false? There exists a 0 1 matrix A such that DRSK A is equal to P comma P for some semi-standard Young tableau P. What do you think?
Correct, ma'am. First question, P
Yeah,
comma
exactly.
P same.
Exactly. In the first question, we got the same P and Q, which is this.
Mm.
And
Mm.
yeah, so this is correct using question A1. Very good. Let's see this one. So A is given to be 1 1 1 0. We need to find dual RSK and RSK of A. So again the same process. Let's do it. Pivot of A is 1 1. First row, first column. So first row, second column. Second column, first row, and just this. Right? And now what we will do, we'll try to find the okay for dual RSK. So we will try to find P dash and Q. So let's do it. So first we'll insert 1. So again, simply 1. And now we insert 2. So we'll get 2 corresponding to that 1. Now we'll insert 1. So when we will insert 1, so 1 has been inserted. So what will bump out? When we
One.
insert 1, exactly. So 1 will bump out and it will go to the next row. So corresponding to that, we'll get 2.
Mm.
So DRSK of A is equal to what? 1 1 2
1 1 1 2
and
1 1 2.
yeah, exactly. We'll just do the transpose. And for RSKA, P and Q we need to find. So again, first 1 1. So first 1 is fine, and then we'll insert 2. So when we insert 2, it will go in the first row itself. That is 1. And now when we will insert 1, now what will happen?
2 will come next.
Yeah, 2 will bump. 2 will be bumped out because we will look for the bigger number, not the one which is equal. That is the only difference between DRSK and RSK. So corresponding to that, we'll get 2. So RSK of A is equal to 1 1 2 and 1 1 2. So yes, this is true.
True.
Exactly. Very good. Let's move to the next question. So we have lambda 2 2 1 and mu is equal to 3 1 1. So these are the partitions of 5. Number 5. Now consider the expression of E lambda. So E lambda as a linear combination of
E lambda equal
symmetric
to
function.
summation m lambda mu into m.
Yeah, and then there will be some constant or whatever. So we'll get something.
Coefficient.
So
n ma'am, capital N lambda mu
exactly.
m mu.
So we know that this is equal to n lambda mu m mu, and mu is a partition of 5, right? Because lambda is a partition of 5.
Wait.
So now we have been asked what will be okay, so mu is a partition of 5 and 2 2 1 mu m mu.
What is?
Yeah, we have been asked what is n 2 1 2 2 1 when mu is equal to 311, because the coefficient we have been asked of mu, where mu is equal to 311. So to find n221 and mu is equal to 311, right? This we need to figure
Yes,
out.
ma'am.
And what is n? N, we know that these are the matrices with uh,
0, 1 entries.
yeah, with 0 1 entries, and the row sum is 2 2 1 and the column sums are 3 1 1. So the row
3,
sum,
1,
yeah,
3, 1, 1.
3 1 1, right? So that we need to find out with 0 1 entries. Okay, so let's try
Yes,
to do
ma'am.
that. We have 0 1 entries. So as you can see, we have 3 rows and 3 columns. 3 rows
Yes, ma'am.
and 3
And 3
columns.
columns.
So what we are sure about, this is 3. So that means these 3 entries must be what?
1, 1, 1.
Exactly. So because 0 1 entries are allowed, we cannot go beyond 0, beyond 1. So it cannot be 2 1 0. So we have just one possibility, that is 1 1 1. Now these 6 places we need to see. Now see this one. So the
Yes,
sum
ma'am.
should be 1. So that means 1 and the other entries must be what? 0. This one,
Yes, ma'am. 0.
right? Because the sum
Yes,
we
ma'am.
want of the third row is 1. So that must be 1 0
Ah.
0. So the only we need to figure out what are these 4 places could be.
Mm.
Okay, so now we know that the sum we want of the first row is 2 and the second row is 2. So we want one of these places in the first row to be 1, or this
Or
yeah. Now we
second
also,
row, first.
yeah, and now we,
Either first row is one, first row,
hmm,
second column or third column. Either second column or third column is 1.
hmm,
And second row, either second column 1 or third column 1.
yeah. So this could be, so either this could be 1 0 or 0 1, and again either this could
Or
be, or I can change the
1, 0
color.
or 0.
So the combination could be 1 0 or 0 1, or 1 0 or 0 1.
1, 0 or 0, 1.
Also one more thing we need to see, that the sum of the column we want it to be 1, right? So
1.
it is not possible that we get 1 and 1 both in the same column. Same for
Yeah.
same for the other one. So what should happen,
Mm.
if the first if these let's see these 4 places. So we have 4 places. So what we want in these 4, just look at these four
First
places
row.
1 1 1 1. We want this, right?
Mm.
If we just
Yes,
see,
ma'am.
we want this. So that means if this is 1,
1,
then this is
0.
0 for sure, and if this is 1, then this
And
has to be
0,
0.
1. 0, 1.
So this is one possibility, and the other possibility. So when we force one place, then all the other places we can figure out. That has just one choice, right? Now again, if we choose this one, if at this place if we put 0, then what will happen?
Mm.
This will become 1, because we want the sum to be like this, 1
0,
1,
1.
and yeah. So
1, 0.
and now we'll get 1 0, right? So what we did, we
Yes,
just
ma'am.
forced this place to be something. So there are only 2 options for this first place, and if we fix this place, then the other 3 places we directly get it. Like there is no other choice for these places if we
Yes,
force
ma'am.
this to be 1. Similarly, if we force this to be 0, then the other 3 places has no choice. This has to be like this only, right? So
Yes,
we
ma'am.
just have 2 possibilities, this one and this one, for this to be true. Like for this number, we just have 2 choices. Is that clear?
Yes, ma'am.
Okay. So from this, what did we got? N 2 2 1 3 1 1. Also we can write it what we got, 1 1 1 and 0 0, and here we got 1 0 and 0 1. The second one is 1 1 1 0 1 1
Zero
0
one
0 0.
10 00.
Exactly. So we just have two options, and that's why this number is 2, which we needed to find
Yes,
out.
ma'am. Mm.
So the coefficient is 2.
2.
Okay? Yeah. Okay. Let's see the next question then. The symmetric function h31. So we have h31. So this is equal to what? What is h31? We know that we can, this is h3 into h1, right?
Yes, ma'am.
Okay, so h3 and h1. So and now we just why I
Oh,
kept this, because we have this relation. So from this relation we know that what are the relation between h and e, the complete symmetric polynomial and elementary symmetric polynomial.
yes,
What
ma'am.
are the relations we have? So from this we know that h1 is equal to e1, and from this, or I can write it from this, h3 is equal to e1 cube minus 2 e1 e2 plus e3, right?
Yes, ma'am.
So what we got, h3 into h1 is, h3 is e1 cube minus 2 e1 e2 plus e3 into e1. So we multiply by this.
Mm.
What will we get? e1 4 to e1 square e2 plus e1 e3. And corresponding to that, what we can write? We can write it to be 1 1 1 1, because this is just this
2
corresponding to
times
this.
of
Yeah.
E11.
So yeah, e211 we can write, if we can write in the increasing order, and here we
Uh,
got v31, right?
yes, ma'am.
Okay, so which one must be correct? Yeah, this one, right?
Yes, ma'am.
Okay, so let's see then the next question. The symmetric function m2 square is equal to what? So m2 square is what? What does that mean? Let's see. M2 is what? M2 is so uh, remember that H and E are different. Like those you can write it as a partition or something, like this is equal to H2 into H2. There is nothing related to M like this, because this does not make any sense. M2 is nothing like M2. What do we know about M2? Okay, M is always a
Mm.
symmetric function corresponding to some partition, right? So let's try to figure out what is this. So m2 is what? M2 is summation xi raised to power 2, right? And I is
Mm.
like 1 to n, whatever, if either it could be infinity, we don't know. So m2 is this. Is that clear? Because 2 is the partition, so we are just saying uh, it will go so m2, so the square, so the first one will get the square, and we have all the permutations to find out this, uh, to make it symmetric, right? So this
Mm.
is always this. And now what is this? If we remember, what is this?
Power
Yeah,
series.
this is the power sum,
Power
that's why I
symmetric.
kept this formula. But yeah, so this is the power sum, exactly as you said. This is this sum, and this is power sum p2,
Mm.
right?
Yes, ma'am.
Okay, so this is p2, and now what we need to find out, we need to find out what is p2, right? So
Mm.
p2 square, so we need to find out, so we got m2 square to be equal to p2 square. Now let's see what is P2. P2 is equal to, from here, as I kept this formula, because we want it in terms of H, right? So in terms of
Yes,
H, we need to see P, how P is related to H. That is with this formula and with this comparison. So we get P2 is equal to this one. P2 is equal to 2H2 minus P1H1, right? And this square of
yes, ma'am.
P2 is this from here. And now what is H2? Oh, sorry.
H1 square, ma'am.
Yeah,
2
yeah, yeah.
H2 minus H1 square.
Why H1? Yeah, yeah,
P1 is
yeah, yeah.
equal to
P1 is
H1.
equal to H1. Yeah, exactly. So we'll get H1 square. And now we can expand it. So we get 4 H2 square plus H1 raised to power 4 plus, sorry, minus 2 into 2, 4 H1 square H2. Now what we can do, we can always write it in the form of uh, partition. So that is 2 square, so that is 2 comma 2 plus H1111 minus 4 2 1 1. Is that clear?
Yes, ma'am.
Right, so we just use the formula and figure out what it will be. So this must be with 4 4, this is this, right?
Yes, ma'am.
Okay, great. So let's see the next question then. For every n greater than or equal to 1, which of the following equations are correct? So yeah, I kept again the generating function formulas because this is directly from there. So the relations are E minus THT is equal to 1. So from there what we got, this product is 1. So that means this sum should be 0, because when we compare
0.
the powers, then this is going to be 1. That means the all other powers are has coefficient 0. That means for all n greater than or equal to 1, this coefficient of t raised to power n is 0. So that means
0.
yeah, the last one.
Third last one answer.
uh, yeah. And so let's see now. Now the relation has been asked for PR and P and H. So P and H has this relation. So again, if we compare the coefficients, we get this. So that is NHN, this one,
Hmm.
right? And if this is true, can this be true? That we need to check. We'll do that. But let's first see this one also. So E and P has the relation with this, and that will give this one. So this is fine. Now we just need to see if this is true or not. If this is true, right? So we can just directly check for some n, because that should be true for all n. We know that this is true, so whether this is true or not, we need to see, because there is this minus 1 raised to power something also. So let's say n is equal to 1, so r is equal to 1, 2 n is equal to 1, so the sum is just for 1. So minus 1 raised to power r minus 1 pr h n minus r. So this will be equal to what? When r is equal to 1, so this sum is just p1 h uh, n minus r, so that means 0 minus 0, sorry, 1 minus 1, 1 minus 1. So we got what? P1 h 0, and the right hand side says this should be 0, so this is 0. And now let's see from here. We'll get again n is equal to 1, that means r equals to 1 to 1, so that means p1 h 0 is equal to what? When n is equal to 1, this is 1 and h1. So this is h1 and this says this is 0. So that means definitely these are not correct, because this is correct, that means this is equal to h1, and h1 is non-zero, we know that. So this cannot be true. So this is wrong. Is that clear?
Yes, ma'am.
Okay. Very good. So A, B, and D are correct.
Day.
Yeah. Okay. Let's see the next question then. Let lambda is equal to 3 comma 2. So lambda is given to be 3 comma 2 and mu is given to be 2 comma 1. The partitions are, so oh, okay. So these are the partitions. This is 5, partition of 5. This is partition of 3. Now consider the expression p lambda h nu. So consider it as a linear combination of elementary symmetric functions. So elementary symmetric functions, right? So let's see, and then find the coefficient of 2 2 2 2. Sorry, coefficient. Right. So firstly, firstly observe that what is happening here. So here, p yeah, so we have given that p lambda and p h nu. So lambda is given to be 3 comma 2 and this is 2 comma 1. So firstly, when you will multiply, we'll get 5 plus 3. So the total degree of any uh, of any like summand of any term of the sum is going to be degree 8 only, because this is 5 and this is 3, so total degree is going to be 8, and that is okay with this also, because E2222 is again 8, right? But we need to check, so this is okay in that sense, but now we need to write it in terms of elementary symmetric functions. Okay, let's see what are we getting. And there is one more thing, there are ways to look at. So for example, p32 is what? This is p3,
P3, P2.
h2 and h1, right? So p3 is what? uh, p3 is this, right? E1q
E1 Q.
minus 3 E1 E2 plus 3 E3. What is p2? P2 is E1 square minus 2
Yes.
E2. H2 is what? H2 is uh, E1 square minus E2, right? This one, this one. And H3 is what? Sorry, H1 is what? H1 is E1. Yeah. So this is the product we are looking at. Now, if we want 2 2 2 2, so what do we want? We want for this is what this is actually okay. So sorry. So this is E2222. This is what? E2, 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 E2. So we want E2 raised to power 4. Let's see, will we get it? So E1 cube, even we are not concerned about. This E2 is here. Here there is E2. There is E2. But is there any E2 here? So what we are doing, we are multiplying these 4 terms. So I can write it. So we have E1 cube minus 3 E1 E2 plus 3 E3, E1 square minus 2 E2, E1 square minus E2 and E1, right? So we want the product to be E2 into E2 into E2 into E2. So as you can see, this is the term for E2, this is a term for E2, this is a term for E2, and there is no term here, right? So when we will do the product, what will we get? That is the major concern corresponding to E2, right? So corresponding to E2 will get this into this into this. So what will we get? E1 and E2 cube, and there is minus minus 2, so we'll get 2 into 2, and there is one more minus, so we'll get this, right? Minus 6 E1 E2 cube.
E1 E2 cube.
So, and this is one of the term we are going to get. So why I am looking at this, because if we just look at these terms, because we want e2 raised to power 4, so we need to make sure that we are at least having 4 power for this. So but here we are not going to get e2 raised to power 4, because we have e1 in the picture and there is no term of e2, though there is no square here which can make it e2 raised to power 4, right? So when we will do the product, we are not going to get e2 raised to power 4. Is that clear?
Yes, ma'am.
Okay. So the coefficient is going to be 0.
Yes, ma'am.
Okay, and if you don't remember the formulas, like basically you just remember this thing, and the all those things will follow. So if you remember this, then you can directly do all these steps, right?
Yes, ma'am.
And
Yes.
there is one. Oh, okay. Yeah, but at least appearing you can check, but yeah, you need to otherwise may do the product and do everything that, like, you can write P3 in terms of xi, x1, x2 in those terms, and again h2, h3, and you can also try to find out the product, but that will be very lengthy. So these are the formulas which can help. Okay.
Yes, ma'am.
Okay, so the coefficient is 0.
Yes, ma'am.
Okay, let's move to the next question then. The symmetric function p3 to 1 is equal to what? So we have p3 to 1. This is equal to, that we need to find out. So as we did last time, what we this is equal to what? This is some mu, m mu, and where mu is what? Mu is coming from the, so we have some partition which is 3, 2, 1. As I explained last time, this is equal to what? This is P3, P2 and P1. So we are actually looking at sum of xi cube, sum of xi square, and like if you want to write jk, we can write xk. So we are doing this product. So what is happening? What can happen? Like for example, you can have x1 cube here, again, yeah, again x1 square, again x1. So you are doing the product over full sum, right? So you might get x1 cube into x1 square into x1. So you will get x1 raised to power 6. Similarly, you will get for x2. So you will get 6 powers. Okay. So what can happen? You can have this 2 degrees clubbed. That means you can have x1 cube, x1 square, and here x2. The third one is different. So you can get 3 to 5 comma 1 combinations, and also you can
4,
get 3, yeah, 4 comma 2.
4, 2, 3, 3,
Yeah. So
3, 2, 1.
yeah, 3, 2, 1. So these are also what you are doing. You can combine these, and whatever all the combinations you are getting, that will give you.
Last time one PDF I showed, ma'am also showing which section, and there we see
Yeah,
in
exactly.
elementary how to convert the symmetric. So using this partition, how to we separate?
I didn't get it. Separate means?
E2, E2, E1, and the next step is S2 X1 square into E2, E1, and again two partition added, one partition leave it, and what is
That
the
was.
possibilities, and we write the symmetric format. Elementary symmetric polynomial equal to, in terms of symmetric polynomial
Yeah, I
we
remember.
wrote.
So that.
I showed, I don't, ma'am, and that
Yeah.
time ma'am explained.
Yeah. This one, this was some product. If I remember correctly, something like this. This was the
Yes, ma'am.
product. So, if, when you have some product, how will you write it? That was the question. So yeah,
Mm,
so that can be done. Yeah, that is some other thing, because that was something like that. And you
mm,
have, for example, sum I think that was sure, or I don't remember
In
exactly.
terms of symmetric
Yeah, in
polynomial,
terms of
S
uh,
SM11 SM22 in S,
in S.
not M. Yes, ma'am. I think
Okay.
yes.
Yeah, that might be. Yeah, so then what would have uh, been used this one? Like you multiply by h1 and then first find this. Yeah, exactly. You will get a function in S. Then you multiply by h2 uh, in
Hmm.
S. Then you get some function of S. Then again you multiply by h2, this h2, and you again
Hmm.
get some function of S. Yeah, so exactly.
Yes, ma'am.
Yeah, when you have to
Hmm.
find out for when you have to write the product in terms of h, in terms of s.
EK means S into 1 power K. SK means we can write HK. So they give HK some partition means in partition type we add now 5,
Hmm.
1, 2. See, 5 means 1, 4, and
Yeah,
2
yeah,
we
yeah,
take 2 plus
exactly.
2, 2 plus 3, and we
Mm-hmm.
elaborate, and finally what we get adding that elements.
Yeah. Hmm. Yeah, that was for the product thing, but yeah, this is something this is different in terms of writing.
Same.
Like that was the induction, like enumeratively you do that, like recursively you do
Mm.
that. Here we just need
Mm.
to find the partitions which we can get from this one. So like we can get 3 to
Mm.
1, and how many times we can get that we also need to write. So for 3 to 1 we can just have one possibility, like we keep lambda 1, lambda 2, lambda 3 in separate boxes.
Yes,
Now
ma'am.
we will just look for the combinations. We can actually combine this 3 2, we can get 5 comma 1, and that is the only
Yes,
possibility
ma'am.
for 5 1, because uh, we
Yes,
cannot have
ma'am.
5 1 with any other ways. So lambda 1 plus lambda 2 comma lambda 3, that is the only possibility for this. This is
Mm.
lambda 1, lambda 2, lambda 3.
Yes, ma'am.
Now what we can do, we can do this one. We can combine lambda 1 and lambda 3, and we can keep lambda 2 in different box. We'll get 4 comma 2, and that is the
Yes,
only
ma'am.
possibility, because we cannot get 4 from any other means like 4 comma 2. Now
Mm.
what we are left with, we can combine all. No, there is one more.
Lambda 2, lambda
Yeah,
3.
exactly. So lambda 2,
3,
lambda
comma 3.
3 comma 3, exactly. And now we can
Now
combine
all.
all three.
All.
Yeah, so we get 3 plus 3 6.
Yes, ma'am.
Right. So these are and these are the single possibilities. So we have these 5
Mm.
possibilities. Now what was the question? So the answer will be just 1 1 1 for all these possibilities. So let's see.
Yes, ma'am.
So this one, because 2 cannot appear, 3
Mm.
cannot appear, so all
Mm.
3 are gone, and we have these. So as we can see, 3 to 1 is there, 3 to 1 is there, 5 comma 1 is there, 4 comma 2 is there, and 3 3 and 6, this is there, this is there. So this is the answer, right? Is that clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, great. Yeah, so we have our answer. Now let's see the next question. Let lambda is equal to 3 2 1. So we have this partition. Consider the expression C lambda H lambda as a linear combination of power sum. Sorry, E lambda, yeah. So E lambda H lambda is a sum of uh, power sums. So for example, let's write this. So this is what E lambda. Lambda is 3 2 1. H 3 2 1. Need to write as the sum of this. Okay, now tell me what must be mu. Mu must be a partition of what?
6.
6.
6, 6, 12.
12, exactly. So it must be a partition of 12, because we are doing the product, and all of these terms are of degree 6, and all of these terms are of degree 6. So the total, when we will do the product, we will get the degree 12, because that is the only possibility. So all the p mu's must be a mu must be a partition of 12. Now what they are asking? They are asking about p lambda. So what does that mean? They are asking about 3 to 1, pt 3 to 1. Can we get this? Like,
Yes, ma'am.
can we get this in the summation?
No, ma'am.
No, because this is 6. This is a partition of
Hmm.
6.
6.
And that cannot appear. We are sure about that. Right? So this is 0. The coefficient is 0, because this is not going to appear. Is that clear?
Yes, ma'am.
Okay, great. So let's see the next question then. The generating function. Yeah, okay, I kept it. So this is I is equal to 1 to infinity 1 plus t xi upon 1 minus t xi. This is equal to what? So why I kept this? Because these are something which we can use here to get our answer. So this is what, so this is equal to, the product we can separate because we are in formal power series. So we have something like this. Xi, I is going from 1 to infinity, into product I is equal to 1 to infinity 1 plus txi. Right? And what is
Yes,
this?
ma'am.
This is
First
exactly
one
first
is
one.
h of t.
So this is h
Second
of
one
t.
is
This is e of t. And what
e
does
of t.
the meaning of their product? This is h.
Then product is 1.
Yeah.
H of t into e of t equal to 1.
Yeah. Yeah, we got this. What did you say? This is 1?
No, no.
No, okay.
No, ma'am. That is.
Yeah, that is the inverse.
Uh, uh,
That is not exactly the product. Then we get that because I think inverse of this. Yeah. So
h t by h dash of t equal to 1. That differentiate and that one, ma'am.
okay, okay.
I'm saying not this one.
Yeah. This is here anyway. Uh,
Mm-hmm.
H. Yeah, this one. E
Uh,
minus t.
yes,
You
ma'am.
do
Minus
minus
t.
t. Yeah, because as you can see, it's just the product. The difference is of minus. So when we do e of minus t, here we will get minus, and then when we will do the product, we'll just all these are will be cancelled out. So we'll get 1. Yeah. So we are in formal power series. This makes sense.
T power n, ma'am. H n t power n.
Where?
Summation n greater
Oh,
than or
okay,
equal
okay,
to
right,
0.
right,
H
right.
n
Yeah,
t power n.
exactly. Yeah. And one more thing, better to, okay, it's fine. So what we are doing, we are now trying to do do this product. So when we take n is equal to 0, what will we get? H 0 into e0, right?
Hmm.
Now the coefficient of t. So the coefficient of t, when will we get? When we will multiply h1. So let's fix this to be 1. Then h1 into e0, because we want the degree to be the sum to be 1, right? So what, when here we will take h1 into t, and from the second summation we take e0 into t raised to power 0, right? So what will we get?
Yes,
h1
ma'am.
e0 into t. And similarly, if we take h0 t raised to power 0, and we take e1 t raised to power 1, then we will get t. So we
H
are,
is equal.
yeah, so what will we get? The coefficient to be h0 e1. Similarly, if we do for t square, so we want t square, so we can either have from the first summand we can have 0 degree t raised to power 0, and from the second we can have 2, and now from the first we can have 1, from the second we can have 1, and from the first we can have 2, and from the second we can have 0. So like we what we are doing exactly, we are just making sure that this sum is 1, sorry, this sum is this degree. So what we are doing exactly, if you okay, so what we can write what we are doing, we are just doing this sum over, so this is 2, so h uh, yeah yeah h n, or maybe let's write hk, then this is h n minus k. N minus k means 2 minus k, and k is going from 0 to till this 2. So this, if we generalize this, we can actually write this whole thing as a summand of over n, and the coefficient will be what? K is equal to 0 to n h k h n, sorry, e, this is e n minus k, and here you have t raised to, okay, yeah, so we get t raised to power n. Yeah, so we get this. Let's see which one is that. Yeah, actually, yeah, this is repeated. Yeah, both are same. So this one is correct. Is that clear?
Yes, ma'am.
Okay, great. Let's see the next question then. The symmetric function nu m3 is equal to what? So m3 is what? M3. The 13th question
Ma'am,
I'll
13
discuss. Yeah.
questions.
The 13th question I'll discuss it later. I like there is some calculation involved. I'll discuss in the end that. Okay.
Okay.
So omega m3. What is this that we need to find out? So yeah, m3 is what? As we wrote earlier, what is m3? M3 is xi raised to power 3.
Summation x to power 3.
So this is going from 1 to n, or it could be infinity. So yeah, this is this. Now what is this?
P3.
Yeah. So why I am going to P3? Because I know that omega of En is Hn, omega of Pn, okay, I don't know, yeah, omega of P, so if we have some lambda, so as you remember, this is something minus 1 raised to power sum of, like sum this lambda 1 plus lambda 2, right? So d, like lambda is a partition of, okay, and minus the length of lambda, right? This was the formula, into p lambda. So what is what this just what p lambda, what omega does to p lambda, it will just whether it will make it minus of p lambda or just plus of p lambda. Okay, so that means, and so we know what omega does, what is this involution does on en or hn or p lambda. We know about all these three. So if we know the expression in terms of p m and sorry, p e or h, if we know in these terms, then we can definitely find out what omega is doing on whatever we have been asked for, right? So as what we did, we wrote it in terms of p3, like in terms of power sum. And what does this do? Now we know that p3 will be what? Now we can actually write it to be just p3, because this is same. What what is this? This is just p lambda 1, p lambda 2. So this p3 we can write it in this form, right? And now what does this do? So this will make it minus 1 raised to power this yeah, so the party which number it is the partition of, which is just 3 because the sum is just 3. So the entry sum minus the length of this partition, that is what, just 1 because length is 1. How many so we are asking for, it is going up to what, like lambda l, we are asking for l is just 1 because there is just one entry. So this is minus 1 raised to power 3 minus 1, and it will just keep p3. So this is what, minus 1 raised to power 2 p3. So we'll get p3, right? Now p3 is there, so we can actually write it again, we can write it back with m3. So this is just m3. Is that clear?
Yes, ma'am.
So this is this. Okay. So let's see the next question then. True or false? For x is equal to this and y is equal to this, is that yes or no? Like, do we have this expression equals to this expression?
Yes, ma'am.
Because
S
this
lambda of
is,
x is equal to a of
yeah,
that
this is,
expansion
yeah, actually this is
summation k lambda mu into m mu.
oh, you are writing in terms of
Expansion S lambda, S
okay.
lambda, X lambda, and B lambda V, and the interchanging now. Lambda V one time, sir, you also teaching last class. Lambda mu into mu lambda means we can write delta.
Yeah, okay, right.
I saw
so,
in notes.
So m and mu, m and h will multiply, will get this, and there is one more option to do that. In terms of x and y, that is also covered in the notes. So that was here. Yeah, this one. So if we begin with, so ht is this, now so what I mean to say, we can write it, we can think of it as in terms of generating function. So ht is this, so this product is this, and so this is equal to this value. Now if so this expression, and look at this expression which we get here, this one. So we get this product to be equal to this. So from this and this expression, we get what we wanted. So m lambda into h lambda is equal to s lambda into s lambda. Is that clear?
Yes, ma'am.
So we can do it in terms of using like using the generating functions. So this is a true statement covered in notes. Okay, let's see this question then. Yeah, so okay, I can do it again. So what we were doing, so we need to find out, so as I said, we need to figure out, because we don't know directly what is this. If we know the formula, we can do that, but right now from the notes we know that what omega does on E is like elementary functions, complete so elementary symmetric functions, complete symmetric functions, and on power sum. We know that what this does on those things, right? So let's see what does this do on Schur function. So let's write what is S331. So this is what we know, that this is equal to k lambda mu m mu. Okay, let's go to monomial symmetric polynomials and try to do that. So we have mu as a partition of, now the sum is 7, so partition of 7. So what do we have? There's one more thing I wanted to say. Okay, like Okay, so you know that lambda square is identity because this is a involution. So
Lambda k lambda equal to 1.
sorry. Uh,
Lambda square means lambda not. So k
no. This
lambda
is
means
omega
1.
square. I'm saying this function.
Mm, mm, mm. I.
So this function is identity. So when we operate it on this, and we if we do omega square, we must be getting as 331, right?
Yes, ma'am.
So what you
Mm.
can do, you can always try like uh, okay, like this is not obviously enough because this always satisfy, and yeah, we need to find out. So this property also must be satisfied, I'm just saying. So yeah, that won't help here, but let's see what does this do on S331. So okay, so mu is a partition of 7, and we have some mu is a partition of 7, and k, the shape we know for a semi-standard Young tableau should be what, 331, right? Because we need to
Mm.
find this cos cup number. So we have 3, 3, and 1. So
Yes, ma'am.
mu could be any partition. So let's so just think of how many we could have. So we have
Involution of S is in S transport, ma'am. Conjecture or what? S dash. W of S is equal to S dash, ma'am.
is that in the notes?
One reference book I saw, ma'am.
Okay. Yeah, like
Mm.
I don't wanted to use that because that was not in the notes. But if
Mm.
you, yeah, actually it's good to have a formula because this process is
Mm.
kind of a bit lengthy. So this
Yes, ma'am.
new S is S dash. S dash means the partition
That
thing.
conjugacy.
Yeah, so
Um,
we have 331. The partition is 331. So there are
we
3 1.
interchange the table is 331, and we
Hmm.
interchange the
Yeah, so
rows
we
are
have, yeah.
columns are
So we'll
rows.
get
This is S.
3 2.
Next we find S dash means
Yeah, 3 2 2. So we have 3 3 1. So the rows will become columns and columns will become row. So this is 3
yes, ma'am.
2 2. Yeah, so we'll get S3 2 2 2. So the answer
Mm.
should be this. So yeah, if you know that, you can definitely
Mm.
use it.
One project book I saw.
Okay.
Someone is
Yeah, I
through the
just don't want to
project.
use that because it was not in
Uh,
the notes. But yeah, actually, it's good to use that
mm,
because what one way is, you can actually write this in terms of mu, and then you can
mm,
try to write mu in terms of e, h, or power sums, and then
mm,
you know what omega does on those things, right? Because and
mm,
omega is a ring homomorphism, so you can use it,
mm,
like you can uh, so uh, so omega of s plus omega of m plus m dash will be equal to omega of m plus omega of m dash, that you can use and find out what exactly is that.
mm.
Now we
Ma'am,
you have
omega
to,
of, okay, omega of E equal to H.
yeah, so using
Omega of
e is
omega
h,
of M equal to P.
no
Omega
no
of
no,
H means what, ma'am?
omega of h is e, omega of e is
Mm,
h, omega like just n, and omega of
mm,
PR, like PR is some PR with some power minus 1 or 1, and these three
mm.
we know. Okay, now what I
Ah,
was saying, you write we don't know. So for mu, this is actually
mm,
forgotten polynomial, that if you know, like that is again not much considered in the notes. So like if you know, you can actually write mu in term, so omega of mu is forgotten polynomial that you can write again symmetric polynomial. Then
yes,
you
ma'am.
can again go to s, and then you can like so if you know mu is f mu, so this is forgotten polynomial. This if you know this, then you can again back to you can again write it in terms of sure polynomial. That is like what I was
Polynomial.
saying, this is a lengthy process, so it's always good to have a formula in this sense. So yeah, if you know
Yes,
omega
ma'am.
s is as dash, then we are done. So
Yes, ma'am.
yeah, so this is the answer as
Mm,
3 to 1. Yeah.
okay, ma'am.
Yeah, this was the last
Ma'am,
question.